Okay. All right. Well, we are now back from lunch. I am Samantha Svitek. I'm one of the committee members. I work at Rockridge High School in Loudoun County, Virginia. I'm a physics teacher there. And to get us going with our first afternoon session, I would like to welcome Carl Mungan. I hope I'm saying that correctly. And he is from USNA, and he will be presenting the modified Atwood machine.
All right, thank you. I was thinking at lunch, how would I motivate this talk? And as usual, my answer is, I don't know. I just find things like this interesting. And I don't know what it's good for, but it's just interesting. All right. So let's start with what are Atwood machines? So I give a kind of a more general definition than maybe just the strict Atwood machine. One or more masses falling while connected by a string and possibly constrained to move along surfaces. So if we look at this probably the traditional one like this, the two hanging masses around a pulley. The one we run a lot in lab, maybe with a cart and a hanging mass. You could have them both at a diagonal. Maybe this one, you say, well, that doesn't look like an Atwood machine. That looks like a yo-yo. Yeah, but if you treat it as a falling pulley, then it's the same kind of idea. Actually, in the 2005 fall meeting, I talked about that as being an Atwood machine. So all of them are examples of exercising, constructing free body diagrams for the translations of the mass and maybe for the rotations of the pulley if the pulleys have mass. And if you want to make it harder, you can put friction on the surfaces. But you end up in all cases with constant acceleration for the masses and constant tension for the pulleys, in the strings. So what happens though if you take, say, the pulley here and you raise it up vertically? And let's keep things not too hard. So the pulley will be massless and frictionless axle, and the table will remain frictionless. Okay, so it's just a modification of the standard kind that we do in lab. And now if you just did this, well, this one starts falling and this one will fall off the edge of the table. So let's just extend the track past the edge of the table just to prevent block one from falling over the edge. Okay, so a couple simple modifications. All right, and here's an example of experimental setup. I just set this up a day or two ago. So the pulley's way up here in the air. All right, here's the hanging weight, M2. There's the rolling cart, M1, so it has low friction. There's the motion detector, so you can see the motion of the cart. And there's the computer running Logger Pro, and here's horizontal track, and I just put two tracks end to end so they would be longer, right? So fairly straightforward using all the standard equipment. And so let's look at how we would analyze this. And there was a paper about this, and that's what motivated me to write this physics education paper, the reference there at the top. And the main trouble that the people who wrote the paper, I don't know how it got through, is they didn't put on their coordinate system, and so they got some of the signs wrong and they got it messed up. Lesson is, if you're going to draw a free body diagram, always put your coordinate axes, otherwise you're pretty much guaranteed you're going to mess things up. So I would suggest, why don't we put the origin at the center of the pulley? That's nice. Then we can go Y downwards to the hanging mass, and we can go X horizontally to the horizontal mass. That makes things as simple as possible. The pulley is a fixed height H above the track. And of course, the snag here now is the string is at an angle theta. And we can figure out what that angle is. It's the horizontal distance X divided by the hypotenuse, which is the square root of X squared plus H squared. All right, and we'll need that later. So that tells us how theta varies as X varies. And the other important constraint here is the length of the string is constant. So that's the length down Y to the hanging mass plus the length, this piece of the string, which again is the square root of X squared plus Y plus h squared. So we can move this square root to the left-hand side. That gives us y as a function of x. If we differentiate twice, that will give us the acceleration of the hanging weight downwards. Okay, and notice again the importance of signs. A sub y is positive in the direction of positive y, and a sub x is positive in the direction of positive x. Clearly, that means one of these has got to be negative and one's got to be positive, obviously, but that's okay. The signs will work out. So we get the acceleration of the falling weight as a function of the horizontal position and horizontal velocity of the horizontal cart. Okay, so we'll need this too. Okay, so now the next step is just write down F equals ma for each of these two objects. Okay, so for the hanging weight, block 2, in the positive direction, we got the weight downwards, m2g. Upwards, we've got the tension, and that's the mass times its acceleration. And now we're going to substitute in that expression that I had for a sub y as a function of x and v sub x. So that will give me the tension now as a function of x and v sub x. Okay, that's fine. Now for block 1, horizontal component of the tension, t cosine theta, that's in the negative direction. So important negative sign there. That's the mass times the x acceleration of block 1. And substitute in this expression for t as a function of x and v sub x. And on the previous slide, we had cosine theta as a function of x. So now I've eliminated all the y's and I've decoupled the equation. Okay, so now I end up with an equation for a sub x as a function of x and v sub x. Only depends on the x parameters of this block. So I decoupled the equations. And I haven't written down that equation for you because it's messy, but it's got square roots and other stuff in the numerator, denominator, but only involving x, v sub x, and constants like h and l and g and the masses. So that's fine. So the problem is, though, it's too messy to solve analytically. So definitely can't solve that equation, but that's not a problem. We just throw it into Mathematica. All right. And here's the parameters taken from the experiment I showed you. So the length of the string I used and how high up my pulley was, where I started the cart. I started it right near the motion detector, started it from rest. And there's the mass of the cart. You probably recognize that standard mass of a Pascal cart. The hanging mass was 100 grams. G, okay. So we're going to be able to figure out what the solution is for x as a function of time. And once you know that, you can just put it in the other equation to find y as a function of time. So now I'm going to ask you to predict what these two graphs look like before I show you the Mathematica solution. So anyone like to tell us what you think these two graphs will look like, roughly, approximately?
Carl, do we assume that the first mass is staying on the surface? Or
Yes,
being lifted up?
yes, that's right. I did check that. It does not get lifted off the surface for these parameters. But that's a good thought. You do have to check that, but it does work out. And experimentally, it certainly works out. So with that in mind, what will it look like? X here is the rolling cart, and Y is the hanging weight. What do you think? Any thoughts?
I would think they should both oscillate.
Good. That's right. Exactly. So there they are out of Mathematica. Okay. So if we look at where is the equilibrium position, that's when both masses would be directly under the pulley. So if you put the rolling cart and just leave it at rest right underneath the pulley, and that by definition was x equals 0, because remember I put the origin here, but it's not y equals 0 for this one. So the y graph is off center, right? But the x graph is centered on 0. Okay, and you can see where the turning points are going to be. So I started it at plus 1.16, and then it's going to go symmetrically to minus 1.16 and then come back. right? So it does in fact oscillate back and forth. It's not exactly a cosine, but it's close. Meanwhile, y is oscillating. The maximum value of y is right at this point here. So just as the rolling cart passes under the pulley, this is the maximum y. So that's the 0.97 that you see up here. Okay. And the minimum is the starting point of the rolling cart. That's when y is at its smallest value, because as m goes back this way, m gets pulled up. So that's at 0.455. And it oscillates twice as fast. So every time the rolling cart goes from here to here, the M2 is going to go all the way through one cycle. So this has got double the frequency of that one, right? So that's nice, and nice thing to do. So next is run the experiment. And if you look at the period here, you can see this is on the order of like 6 seconds or something for the rolling cart. I was just measuring the rolling cart. So for the rolling cart, there it is, and it's on that order of 6 seconds. So there's a good agreement with the period. The amplitude does decay away, and you notice that it decays away pretty much linearly. That's characteristic of friction, either kinetic friction or in this case, rolling friction. Will give you, as you may know, a linear decay. You get exponential decay if you have a drag proportional to the speed, but for friction, which is speed independent, you get just a linear decay in the amplitude. So that's how that works out. And so here's some things that could extend this. So we could certainly add in the rolling friction in the theory. That would be a nice thing to add in. We could, if we wanted, add mass and moment of inertia of the pulley. I was thinking we could put a force sensor on top of the cart. That way you could measure the tension, or maybe you could make the hanging weight the force sensor, so you could directly measure the tension instead of just this X component. If you want to make some of those other modifications, maybe we could tilt the track, or the hanging weight could be a second cart on another tilted track. So I stopped there, and you can find a write-up of this on my webpage, or you can always email me. So thanks for your attention.
Thank you so much. I think we are now open for questions. There is one in the chat from James Frericks about the wrapping of the string around the pulley and how you're accounting for that. Along with the contact point of the string on the left, it moves as the cart moves.
Okay,
this is
so,
back the results.
Yes, it wraps a little bit around the pulley, but not much. And so it's not enough that it's really a problem. It's true there's going to be an extra like half circumference as it goes around the
Yeah,
pulley.
I was really wondering, because the constraint you wrote down is a little bit too simplistic. I mean, and you know, of course, if it was just adding a constant because the string is wrapping around the pulley,
Yeah,
that wouldn't affect anything. But because the contact point is moving, it could have some effect on the motion.
it could. You're right. So
Yeah.
it only wraps though an extra half circumference, so it doesn't keep wrapping. It just wraps once, and then when it
And your
comes back,
pulley is very small compared to the size of everything else.
it's
Is
the
that the key?
standard little Pasco black, very light pulleys here. Again, you see it in the picture here. It's just one of those things. These are very lightweight and very low frictions.
Yeah,
It's a tiny correction. So yeah, as the cart passes, it wraps underneath there, and this doesn't actually fall below, but you can slide the pulley over sideways if you're worried about it hitting the track. So it just misses the edge of the track there.
Oh, I might be missing something. What's causing the oscillation? I don't see it.
Well, because when it passes through the equilibrium position, it's still moving. As it starts moving to the right this way, it starts pulling the mass back up. And then once it gets to the end, right?
I see. I see. I didn't know that the cart on the track is actually going past the pulley. I didn't know that. Oh, okay.
So the cart oscillates back and forth like this. Here's the 0 point is right here in the center. So it starts right near the motion detector here, about a meter away, and then it goes a meter this way. And then, meanwhile, the mass is oscillating up and down like this.
Oh, that's great. I like this. Thank you.
Yeah, the people who wrote the original paper on this, they got it wrong. Because they messed up their signs, they ended up getting a solution where everything just goes to infinity, and that's not right. But we can all make these mistakes if we're not careful with signs.
A little surprising it got published, though.
Well, unless you carefully look, they showed only a portion of the experimental data. They didn't extend the track, so they stopped it once it reached this point. And it seemed to match their theory. And no one noticed.
Interesting.
Kyle, you ever think of attaching a spring? It's going to be spring to the horizontal mass?
No, but.
A little bit more complicated, I guess.
Yeah. I mean, there's all kinds of variations maybe you can do.
I do have to interrupt to move us on. That was wonderful. Thank you so much.